Let's consider this example that states, let vector q equal to 3i plus 4j. Find the magnitude of vector q. So this notation indicates the magnitude of vector q. So let's consider our x and y axes. So y-axis, so x-axis. This vector says 3i, so we know the 3 magnitude in the I direction is, let's show that with another color. This is 3i, 4j as such, and we got 4j here. So now we know that 3i, so this guy, plus 4j, we're doing head to tail addition. So this would be 4j, would be our resultant vector q. What we're trying to find is the magnitude of q. So for a two-dimensional vector like the one we are seeing here, the magnitude of that vector is the square root of its x component squared plus its y component squared. So when we apply that to here directly, this is the scalar. Qx is a scalar quantity because we know the direction is I because we're talking about the x direction. So we are looking at this quantity right here for the value of Qx, and for Qy, we are looking at this value, which is 4. So then we directly apply that. We have 3 squared plus 4 squared, which will give us 9 plus 16, which is square root of 25, which is just 5. So we found the magnitude to be 5. So now let's follow up this question with a very important one, which states, find a unit vector that is in the same direction as vector q. What is a unit vector? It is defined as a vector that has a magnitude, so let's denote the unit vector with the letter u, a magnitude of 1. Any vector in any direction, let's say we have a three-dimensional coordinate system with our z, y, and x. A unit vector can be pointed in any direction, this direction, that direction, so on. As long as the magnitude is 1, similarly in a two-dimensional, let's give two-dimensional system. It could be like this, like that, like this, like that, so on. As long as the magnitude is 1, it is a unit vector. So what we want in this question is we want a vector that is the same direction as q, just a magnitude 1. So let's see how we can do that. From the definition above, we knew that q looks like this. So q is 3i plus 4j, right? So in order to find the unit vector of q, we need to use the following formula. We get vector q, this is our vector q, and we simply divide it by its magnitude. And here's what will happen. We will get 3 over 5 I hat plus 4 over 5 j hat. Let's check if the magnitude of our unit vector is 1 or not. This is what we got with the formula. So let's see. We will do the square root of 3 over 5 squared plus 4 over 5 squared, which is 9 over 25 plus 16 over 25. You will see that 9 plus 16 is 25. Dividing that by 25, we get 25 over 25, and the square root of 1 is 1. So as you can see, this formula works. A quick recap here. The question asks, find a unit vector that is in the same direction as Q. So we got Q, and we divided it by its magnitude. We divided the vector by its magnitude, and then we got this expression, which we later checked whether its magnitude is 1 or not, and then we confirmed that it is 1. So this is our answer. This is a unit vector that is in the same direction as Q. Because again, the reason why this is in the same direction as Q is because we have this vector, right? And when we divide a vector by a scalar means this is just a number. This could be like 2.33 or like, in our case, it was 5. We basically divide the vector by a number, so its direction doesn't change. When I show that graphically, let's say we have this vector, right? So I'm going to show this graphically really quick. So let's say we have our vector q. Its magnitude is 5, and if this is the x-axis, the angle it makes is, let's say it's theta, right? So I make another vector, and this time it's much shorter, right? Because its magnitude went from 5 here to 1, because it's a unit vector now. However, let's look at the angle it makes. This is the x-axis. The angle is still theta. The angle is still theta. The only thing that has changed is the magnitude of this vector. Its direction is still the same. So this is basically what we have done with this calculation. And now we will consider a very similar example. This time it will be in 3D. And again, you will notice that there's barely any difference in the way that we will approach this problem. And because this is going to be pretty easy and not very different from the previous problem, I will go through it fastly. Again, the problem states find a unit vector in the same direction as f, which is defined by 2i plus 7j plus 1k. So let's draw a sketch really quick just to visualize. And this is our z, y, and x. So let's see what this vector does with a different color. It goes 2 units in this direction. Then it goes 7 units in the y direction. Let's make that better. And then it goes 1 unit in the z direction. So 1 unit here. So let's draw our resultant vector. Our starting point is here and our end point is here. So I'm going to draw a straight line from here to there. Could be better. Okay. So this is our vector f. This is what it looks like. So to get the unit vector f, we want vector f divided by its magnitude. We don't know the magnitude of vector f, but we can calculate it, so let's do that. So we have 2 squared plus 7 squared plus 1 squared, which gives us 4 plus 49 plus 1, which is the square root of 54. So then let's calculate our unit vector. 2 over square root of 54i plus 7 over square root of 54 j plus 1 over square root of 54 k. So this is our answer. And now I will do a follow-up on this answer, and the question will be the following. What are the direction cosines of vector f? So what is this new thing? Let's define what direction cosines are. Let's say we have a vector A that exists in R3. So it has 3 dimensions. So it could look like this. let's say 3i plus 4j plus 2k. So this is a three-dimensional vector. It has three components. So let's get a unit vector for vector A. We just did this in the previous example. It would be vector A over the magnitude of vector A. That would give us the unit vector of A. So a vector that is in the same direction as A, but it is not the same magnitude. Its magnitude is 1. So we can show the unit vector in the following form. The unit vector of A can be shown as the x component of A divided by its magnitude in the I direction, plus the y component of A divided by its magnitude times j hat, plus the z direction over its magnitude and k hat. This can also be shown, this expression right here, in the following way, which looks like this. The unit vector of A is cosine alpha in the I direction plus cosine beta in the j direction plus cosine gamma in the k direction. So these two equations can be interchanged. The reason is, when we look at the graph of a cosine curve, it will look like this, where the top bound is 1 and the bottom is 0, obviously. So the output of these functions cannot be greater than 1. This actually works very well with this unit vector concept, because if we have, let's say, a unit vector b that has magnitude for I, j, and k, the magnitudes, let's say 1, 0, 0, right? It'd be 1, 0, 0. The magnitude of this is 1, because 1 squared plus 0, 0 is 1. The value of this is 1 plus 0 plus 0, so that's 1. But let's say if we had, let's say 2, 0, 0, then we're looking at a magnitude that is equal to 2. So you will see that the highest number that the scalar in front of one of these direction vectors can get anyway will be smaller than 1. So this makes sense. The fact that we're using the cosine function here makes sense, because for a unit vector, our scalar value in front of our direction will be smaller than 1 anyway, or 1. So now that we have established that these values will be smaller than or equal to 1 anyway, and we see that the cosine function can output such behavior, then we can consider applying this to vector f, which up here we determined so we have unit vector f right here, the unit vector f, pretty important. So we see a certain similarity here. This and this guy look pretty similar. We calculated unit vector f in this form right here. The question is asking us what are the direction cosines of f. So basically asking what is alpha, the angle alpha, what is the angle beta, and what is the angle gamma. So we see that these two expressions are equal to each other. I've mentioned this many times at this point. And we can utilize that to figure out these angles, because we know that in the following expression, cosine alpha equals 2 over the square root of 54, what we can do to find alpha is to utilize the arc cosine function. Arc cosine function can be utilized to give us alpha. So let's do that for every angle that we have. We did that for alpha. Let's do it for beta. For angle beta, cosine beta is equal to this value, which is 7 over 54, which gives us beta. And let's do the same for gamma. Cosine gamma up here is equal, cosine gamma is equal to 1 over 54. So that will be 1 over 54 cosine 1 over 54 is gamma. And I'm going to go ahead and put these into the calculator really quick. We get the following values. This is 74.2 degrees, this is 17.7 degrees, and this is 82.2 degrees. Why is this important? Why are these angles important? Let's show them graphically. So let's say we have a vector and our vector looks like this. What we will see is between the z-axis and our vector v1, let's call it, between the z-axis and v1, the angle will be gamma. Between the y-axis and v1, the angle will be beta. And between the x-axis, I'm just going to scroll down a bit, between the x-axis and v1, which is this nice angle right here, the angle is alpha. So that's why direction cosines are important. It's because they can give angular data about the direction of a vector. So let's do a quick recap on what we've done in this video. We have established that for two-dimensional vectors, the magnitude is the square root of the x component of the vector squared plus the y component of the vector squared. For three-dimensional vectors, very similar. The magnitude is the x component squared plus the y component squared plus the z component squared. A unit vector, which is often denoted with a u, can be calculated as follows. Let's say we have a vector c. The unit vector for c, denoted by u sub c, is equal to the vector c divided by its magnitude. So the vector c divided by the magnitude of vector c. That vector will look like, if it's a three-dimensional vector, its x component over its magnitude, so on and so forth, will be analogous to this form that is related to direction cosines. Sorry, I forgot to add this in here. This is important because a unit vector is a vector, so we need to not forget those. The direction cosine, that is the exact same thing as this unit vector here, UC, will equal cosine alpha plus cosine beta plus cosine gamma. And we can find alpha, beta, and gamma as follows. And that's all for this video, and have a nice day.